study about the instruction execution in the 8085 microprocessor and the timing diagram of the various cycles in 8085. So let's start with our topic. As we know that the microprocessor, it is a programming device. So if the user want to use the microprocessor for various applications, then he or she has to write the programs in the 8085 for various applications. Now, to write the program, the user should have knowledge about the programming knowledge, the programming language, and the instruction set of the microprocessor. Now, the instruction set, it contains various instructions. Instruction means that various types of operations which a microprocessor can perform, like addition, subtraction, then logical operations like AND, OR. So, various types of operations which a microprocessor can perform, they are collectively made a set in the instruction set. Now, the instructions of the microprocessor, they contains two parts. First is the opcode and second is the operand. So, any instruction which is written in the microprocessor in the program, it will have two parts. First is opcode and second is operand. Now, opcode, it means it is a command, or we can say that it is the operation which the microprocessor is going to perform. Like if the microprocessor, it is performing the addition, then we have add, then for subtraction we have sub, for and, that is the logical operation, we have ana, ani. So these are the machine codes, that is the opcode, the operation which the microprocessor is performing. Then operand, it is the data, or we can say it is the object on which the operation is to be performed. Now this operand, it can be either a data, that is it can be a number, and 8-bit data, 16-bit data, any of the data can be there, and it can be either a register or a memory location. Okay, so these are the operand on which this operation has to be performed. So any of the instruction in the microprocessor, it will contain two things. First will be the opcode, that is what operation the microprocessor has to perform, and second is the operand, the object on which the operation has to be performed. Now, when the microprocessor, how it is working, first the microprocessor, if any instruction is written, then microprocessor, it will first fetch that instruction. Fetch means it will fetch the instruction from the memory, because in the memory we are writing the program. So the microprocessor, it is going to fetch the instruction, the first instruction of the program, then it will decode that instruction. Decode means it will change it into the machine code, because the microprocessor, it is a machine, so it is going to understand the machine language only, but we are writing the program in assembly language, that is in the form of mnemonics, because like if we are writing add or we are writing sub, we understand that it is an addition operation and it is a subtraction operation, but how the machine is going to understand it, it will convert this add into the machine code. Like if its machine code is 3e, then this decoding register, what it is doing, it is converting the assembly language into machine language. It is converting every opcode into its machine code, and then the microprocessor will understand that now this 3e means that addition, and microprocessor has to perform the addition operation. So second thing, what a microprocessor does it, first it will fetch that instruction, then decode that instruction, and then it will execute that instruction. Execute means if it is written there that addition, then 3e means it has to perform the addition operation, and it will add the two numbers which it has to add. Like if it has to add the accumulator and an 8-bit data, then the addition will be performed and the result will be stored in the accumulator. So last step will be execution of that instruction. So these are the three steps which the microprocessor does. First is fetching, second is decoding, and third is executing the instruction. So in this video, we will study that how the microprocessor, it executes the instruction. Okay. Now before starting with the execution of the instruction, there are few terms which you should understand. First is instruction cycle. Second is machine cycle. And third is T-state. These are the three terms which are used in the execution of the instructions. Now, instruction cycle, it means the time taken by the microprocessor to complete the execution of one instruction. The time which the microprocessor is taking to complete the execution of one instruction is called the instruction cycle. Machine cycle means the time taken by the microprocessor to complete one operation, because there are various operations performed by the microprocessor. Like the microprocessor performs the memory read, memory write, input output read, input output write, opcode fetching, opcode decoding. These are all various operations performed by the microprocessor. So the time taken by the microprocessor to complete the execution of one operation is called the machine cycle. So let's write the definition of instruction cycle and machine cycle. So instruction cycle is the time taken by the processor to complete the execution of an instruction. So it is the execution time of one instruction. Then we have machine cycle. So machine cycle is the time required to complete one operation, and that operation can be either accessing the memory or the input output device. Because when an instruction is executed, there are various operations involved in it. Whether it can be like the microprocessor has to read the memory, or it has to write the result into the memory, or it has to read the data from an output device or get in data from an input device. So there can be any of the operations. So time required to complete one operation is called the machine cycle. Then we have T states. T state is the time corresponding to one clock period. Now the microprocessor operations, they are synchronized with the clock pulses, because we know that the 8085 microprocessor, it is working at the clock frequency 3.5 megahertz. So this clock frequency, this clock is the crystal connected to the 8085, it is providing the clock pulses. So the time which is equal to one clock period is called the T state. So we can say this T state, it is the basic unit to calculate the execution of an instruction, because we have to measure the time. Now how we are going to measure the time? We will compare it with the clock period. So time which is equal to one clock period is called the T state. So we can say that it is the basic unit it is the basic unit to calculate the execution of instructions in the microprocessor. Now the complete execution of an instruction, this is an instruction which we have written in the program of the microprocessor, and this instruction execution, first it will comprise of the instruction cycle, time required to complete the execution of one instruction. Then in this instruction cycle we can have various machine cycles, because any of the instruction, it will involve various operations. So time required to complete one operation will become the machine cycle. And in this machine cycle we have various T states, because T states means one clock period. T state and clock period, they are one and the same thing. So T state, it means one clock period. So in machine cycle we have various T states. Now in an instruction cycle we can have 1 to 6 machine cycles. And in machine cycle we can have 3 to 6 T states. Okay, so T state is within the machine cycle, and machine cycles are within the instruction cycle. So the execution, the complete execution of the of an instruction in the microprocessor, it is divided into the various cycles. First is the instruction cycle, then we have machine cycle, and in the machine cycle we have various T states. So now we are going to study the various machine cycles which are in the 8085. First, let's have a view on the various operations performed by the microprocessor, because we are saying that machine cycle, it is the time required to complete the execution of one operations. So let's see that what are the operations which are performed by the microprocessor. So to execute a program, the 8085, it performs various operations. First is opcode fetch. Then it has the operand fetch. So any instruction, it will first, the microprocessor will fetch the opcode, then it will fetch the operand, and then it will perform the memory read or write, or either input output read or write operations. So these are the various operations which the 8085 processor, it performs. Now how the processor knows that it has to perform opcode fetch or it has to perform memory read write? How it is knowing? It is knowing the that which operation it has to perform through the status signals. status signals, that is S0 and S1, they define that which of the operation the processor has to perform. So let's see the table that how the status signals they define the operation. First we were having opcode fetch. The operations, because it is the machine cycle, so we can say that there are 5 machine cycles in the 8085. So these are the machine cycles we can say. First is opcode fetch, second is memory read, third memory write, so there are 5 machine cycles, or we can say 5 operations performed by microprocessor. So opcode fetch, we are defining here the status signals. The first status signal we have input output or memory, then we have S1 and S0, and here we have the control signals. So in the opcode fetch machine cycle, input output memory, it is a memory operation, so its value will be 0. S1 and S0, if they are 1, both are 1, then it will be the opcode fetch operation, and it is the RD bar signal, it is 0. So what the signals? First is the input output and memory signal, then S1 and S0, and the read and write. These signals, they decide that what type of operation the processor has to perform. Now for memory read, this should be 0, because M bar means it's an active low signal and it is an active high signal. So active low, that it means its value is 0, so it will be a memory read operation. And S1 and S0, they will be 1 and 0. S0 should be 0 and S1 should be 1, and it is a read operation, so RD bar signal is 0, it is active. Bar means that signal is active low, okay, that is it is active when its value is 0. Then memory write, so it is again a memory operation, so its value will be 0. S1 and S0, it will be 0 and 1. It's a write operation, so WR bar is active. Then we have input output read, so input signal should be active, that means it is active high 1, its value should be there. S1 and S0, it will be 1 and 0. Then we have control signals, that is read, so RD bar should be 0. Then we have input output write, so input output write, this should be 1. Then S1 and S0, its value should be 0 and 1. And for this write operation, WR bar is active. So these are the values of the various signals which are defining that which type of operation the processor has to perform. So these status signals, the input, output and memory and S1, S0, they are defining that which of the machine cycle is being right now performed by the microprocessor. So let's study each of the machine cycles one by one. First, we will start with the opcode fetch machine cycle. The first operation performed by the microprocessor is the opcode fetch. The microprocessor, it fetches the opcode from the memory and then decode it and then execute it. So the microprocessor, it is going to fetch the opcode from the memory where it is stored, and then it is going to decode and then it's going to execute it. Fetching means to get that instruction. Okay, so the microprocessor, it needs to get the opcode. Opcode is also the machine code. So opcode fetching, it is the first operation, and the microprocessor, it need to fetch the opcode which is stored in the memory register before it is starting any type of execution of the instruction. So for every machine cycle, we have the timing diagram, because we know that each machine cycle, it consists of various T states. So in each T state, what operation or what function the microprocessor is doing, how it is completing the execution of an operation, it is shown in the timing diagram. So there is a timing diagram associated with each machine cycle. So for this opcode fetch machine cycle, let's see what's the timing diagram. What is the timing diagram of the opcode fetch machine cycle? Let's draw it. In this site, because machine cycle, it consists of various T states. So here T1, T2, T3 and T4, these are the T states. The opcode fetch machine cycle, it consists of 4 to 6 T states. So here we are drawing 4 T states here. These are the signals. So how the signals are changing during these 4 T states. Because each t state, it is equal to one clock period, so we are drawing one clock in one t state, then we have another clock in the second t state, similarly third clock and fourth clock. So one clock period, it is equal to one t state. This is A8 to A15, the higher order address bus. So this is the timing diagram of the machine cycle. You can see here that you have 1, 2, 3, 4, 5, 6 signals here shown. First is the clock, because one clock is equal to one T state. Then we have higher order and lower order address bus. You know that the lower order address bus, it is multiplexed with the data bus. So this is showing both the data bus and the address bus. How you can differentiate that whether it is a data or it is an address, this is shown by this ALE signal, address latch enable. If it is 1, it means that address is available here, and if it is low, it means data is available here. Then we have input output or memory, and then S1 S0, the status signal, and then we have the read signal. So in this opcode fetch machine cycle, here we have available the higher order memory address. Here we have the lower order memory address. This is our opcode, or we can say the data. This is address latch enable. Then we have input output and memory. Because it is a memory operation, so its value will be 0, and it is an opcode fetch machine cycle, so S1 and S0, they both are equal to 1. And this is a memory read operation, so read signal, it is low in the opcode fetch machine cycle. So you can see that the buses, they are shown as a two lines which are parallel to each other, and they are crossing over with one another, because there are some lines which are high and some lines are low, so they are shown as two parallel lines. Now this dash, it is indicating that the processor or the line or the bus, it is in the high impedance state. So this dash line is denoting the high impedance state of the bus. If it is like this, it means the value of the signal is high. If it is a straight line which is lower than the level, so it is showing that the signal is low, its value is 0. So these are the various signals in the opcode fetch machine cycle. Now let us see that which operation or which task will be performed in each of the T state. First we will start with the T1 clock period or T1t state. Or we can say it is a clock cycle. In the T1t state, the contents of the program counter, they are placed on the address bus. You can see that the address bus, the higher order address bus, it is having the higher order memory address, and the lower order address bus is having the lower order memory address. So the contents of the program counter is storing the address of the next instruction. Wherever the next instruction is written in the memory, that address is stored in the program counter, and that address will be loaded on the address buses in the first T state. The contents of the program counter is placed on the address bus. We have A8 to A15 as the higher order memory address. The higher order bits will be stored here. And AD0 to AD7 will have the lower order memory address, or we can say lower bits. So if the address is like 8050, So 80 is the higher order memory address. It will be stored at A8 and A15. It will be loaded at there, and 50 will be loaded at the lower order address bus during this T state. Second, the input, output and memory signal. Next, you can see that in this machine cycle, the input, output and memory signal, it is low, and S1 and S0, their values are 1. Okay, so this is low because this opcode fetch machine cycle, it is a memory operation. The address, it is being fetched from the memory location. The address of the memory location or the opcode we are fetching from the memory location. So it's a memory operation. Its value will be 0, and S1 and S0 will be 1 because it is an opcode fetch operation. Now next, this ALE signal is high during this T1 state. It means that this multiplexed address and the data bus, it is acting as the lower order memory bus, lower order bus. So here whatever data is available, it will act as the lower order memory address. Okay. So this was about the T1 state. Next we have the T2 state. We will study all the signals, how they are changing during the T states. So in the T2 states, you can see that this ALE signal is low. So whatever data is available on this AD0 and AD7, this multiplexed address and data bus, it will now act as the data bus because ALE has now become low. ALE is low. So AD0 to AD7, it will act as the data bus. So you can see that in this T2t state, the RD bar signal, it is made low by the processor. So it is indicating that it is a read operation. And this signal makes the memory device load the data bus with the contents of the location addressed by the processor. The address is being already fetched by the processor, higher order and lower order memory address. So whatever opcode is written at that memory address, that will be fetched by the processor and it will be loaded on the data bus now. So here opcode is available now because ALE signal is low. So this was the T2t state. Now in the T3t state, you can see that the opcode is available on the data bus, and still the read operation is low, and here higher order memory address is available up till 3.5 T states. So now this opcode will be, it is already fetched, so now it will be decoded and executed by the processor in the T3T state. So during this T3 cycle, this read signal, it is showing that opcode is available here. So this will be synchronized. This opcode will be read by the processor and moved on to the instruction register. So now the instruction register, it is having the opcode which is available on the data bus. So here you can see that this opcode, it will go to the instruction register. And also in this T2t state, this RD bar signal, first it was low, then it is made to equal to 1. So now this is deactivated. That is, read operation has been finished, the opcode has been read by the processor and it has been sent to the instruction register. So this was done in the T3t state. Now in T4t state, the opcode has been shifted to the instruction register. Now the instruction register, it is going to decode the opcode and then it is going to execute that instruction. Whatever operation is being associated with that instruction, that will be executed. So the processor, it is going to decode the instruction which is there in the instruction register and it will generate the necessary control signals to execute the instruction, because after decoding, the execution will take place of the instruction, and based on the instruction, further operations takes place, like if it is a memory read, memory write, or input output read, input output write, then those operations will be performed based on the instructions. Now let's take an example of an instructions that how this opcode fetch machine cycle takes place. We have here, let's take an example of the instruction which is written at the memory location 2005H. H means that this address, it is in the hexadecimal notation. So 2005, it is written, it is the memory location, and at this memory location we have the instruction move C comma A. This instruction means you have to move the contents of the accumulator register into the C register. So it is a copying function it is performing. Now this move C comma A instruction, it is having the opcode 4F H. H again means that it is in hexadecimal notation, and 4F is the opcode or we can, sorry, opcode not, it is the machine code for this instruction. So microprocessor, it understands only this 4F, it doesn't understand move C comma A, it is the language in which we are writing the program. And the microprocessor, it is going to convert it into the machine code and it will understand 4F. So this 2005, we have the higher order address as 20 and lower order address as 05. So in this opcode fetch machine cycle, the higher order address, that is 20H, will be stored in this, and lower order memory address is 05H, it is stored here. And the opcode for the move C comma A is 4F, so it will be loaded here. So microprocessor, In the first T state, when this ALE signal is high, it means lower order memory address is available. 20 and 0FH, it is going to read, and there this opcode is written. 4FH, it is going to fetch that opcode, and then that opcode will be decoded and further instructions, that is the moving operation, will be performed. Then the contents of the accumulator, they will be copied into the C register. So this was the opcode fetch machine cycle. Okay. The next cycle we will study is the memory read machine cycle. This cycle, memory read machine cycle, it is executed by the microprocessor when the processor is performing the read operation, when it has to read any data or any of the contents from the memory. So at that time, this machine cycle is executed. This cycle is exactly the same, just like the opcode fetch machine cycle, because in opcode fetch machine cycle also the memory read operation has been performed. Now, this cycle, it has 3 T states, unlike the opcode fetch was having 4 T states. Here we have 3 T states. And the signals S1 and S0, they were 1 during the opcode fetch machine cycle. Here S0 is set to 0. Okay, and S1 is 1. So this is the status signals, value of the status signal. Let's see the timing diagram of the memory read machine cycle. Let's draw the timing diagram for it. As the memory read machine cycle, it consists of 3 T states. So we have here T1, T2 and T3. And here we have the signals. Okay. Again, we will draw here the clock and ALE signal, higher order and lower order memory address bus. So in this memory read machine cycle, you can see that it is 3 T states. It requires 3 T states. In the first T state, because each T state is equal to 1 clock period, so 1 clock pulse is drawn here in 1 T state. In this first T state, we have the higher order address available on this AH to A15. Then we have the lower order memory address available at AD0 and AD7. They are multiplexed address and data bus, and when this signal ALE is high, it means that whatever data is available on this bus, it should be considered as the lower order memory address. That means this bus acts as the lower order address bus. When this signal is low, it means this bus is acting as the data bus, and whatever data is available, it is that 8-bit data. Now this input, output and memory, because it is a memory operation, so this m bar, it is value is equal to 0, and this cycle is the memory read machine cycle, so S1 is 1 and S0 is 0. So this is the value of the status signals. Then we have RD bar, because it's a memory read of cycle, so read operation has to be performed, so read signal is low. This means this signal is active during this T2 and T3 T states. So whenever any operation, any instruction is written in which memory read operation has to be performed, so that operation will require 3 T states. Let's take an example of an instruction so that you can clearly understand it. We have an instruction MVIA 32H. H means again the hexadecimal notation. So this MVIA, this instruction is having the opcode 3E. And this opcode is written at the memory location 2000. Okay. And this next, the data, because what this instruction means, you have to copy or you have to move the immediate data which is given in the instruction to the accumulator. So accumulator contents has to change to 32. So this is the data which you have to use. So this data is given at the next memory location 2001H and 32H. So in the memory of the microprocessor, this is how we save the program. So we have first operation associated with every instruction is opcode fetch, because every instruction will have an opcode and that opcode has to be fetched from the memory. So first opcode is 3EH, so first cycle will be opcode fetch. Next, when the microprocessor gets this 3E opcode, then it will understand that it is a move operation and it will require a data which has to be moved. Now this data, it is stored at this memory location, so next cycle will be memory read. So this data will be read from the memory, so second cycle will be memory read. Now opcode fetch, we have already studied, it requires 4 T states. And memory read, we have studied here, it requires 3 T states. So total T states which are required by this instruction to be executed, they are 7 T states. 4 T states for the opcode fetch and 3 T states for the memory read. So when we are asked to draw the timing diagram for this instruction MVIA 32H, then first we will write the 4 T states. We will draw the 4 T states for the opcode fetch and 3 T states for the memory read. Let's see how we are going to draw the timing diagram. There are many questions asked in the universities for drawing the timing diagram and how many T state this instruction will require and how much time it will take. So let's see that how those questions can be solved. We have 7 T states. So here we are going to draw 7 T states for it. These T states should be of equal duration. Here we are going to draw all the signals, clock, and then the higher order address bus. Now, first four T states are for the opcode fetch, and last three T states are for the memory read. So what you are going to do first, draw the opcode fetch machine cycle. You know the timing diagram for it, and then draw the timing diagram of memory read. So first you have written the at this memory location 2000 we have the 3EH. So 20 is the higher order address and 00 is the lower order address. So you have 20H higher order address and 00 the lower order address, and at this memory location you have the opcode 3EH. Then this is ALE signal is high, it means we have address. If it is low, it means it's a opcode or it's a data. Now this input output at memory, it is 0 because it's a memory operation, and S0 and S1 they are equal to 1 because this is an opcode fetch machine cycle. This read signal is low, it means we have to read this data from this location. Okay. Now next we have the memory read. So next you have to read the data from the memory location 20 and 01. 20 will be here because it's a higher order bits, and next we have 01H, and at this location we have the data 32H. Then this input output and memory, it will be 0, S1 is 1 and S0 is 0 because it's a memory read machine cycle. Again we have read signal as 0, indicating that it's a read operation. So this is the complete timing diagram of this instruction MVI A32H. It is requiring 7 T states, 4 for the opcode fetch and 3 for the memory read. So whenever you are asked to draw the timing diagram of an instruction, every instruction will have this opcode fetch machine cycle, because first operation the microprocessor performs is to fetch the opcode. Second, you have to decide that whether it's a memory read, memory write, input output read or input output write operation, and correspondingly for that machine cycle you have to draw the timing diagram. So here we have we can judge that it's a memory read operation. So we have drawn the timing diagram for the memory read machine cycle, and the complete timing diagram we have obtained for this instruction. Now, if we want to calculate, if it is asked to calculate the time required to complete the execution of this instruction, then how you can calculate? We know that the clock frequency of the microprocessor, it is 3 megahertz. So if clock frequency is not given in the question, then you will take 3.5 megahertz, so 3 megahertz. And if it is given in the question, then you will take that clock frequency. Now suppose here we have given the clock frequency as 2 megahertz. Now we want to calculate the clock period, because we know that 1 T state is equal to 1 clock period. So clock frequency is given, we can easily calculate the clock period. It is 1 by f. So it will be 1 by 2, or we can say 0.5 microseconds, because here we are given the frequency in megahertz, so it will be in microseconds. Now 1 T state is equal to 1 clock period. So for opcode fetch, we were requiring 4 T states. So what we will do, we will multiply 4 with the 1 T state, that is 1 clock period, or we can say 0.5 microseconds. So it will be 2 microseconds. Then we have memory read, 3 T states. So 3 into 0.5, it will be 1.5 microseconds. So total execution time of the instruction MVI A32H, this instruction execution time, total time required to execute this instruction is 2 plus 1.5 microseconds. So it is 3.5 microseconds. We can directly also obtain, we can have 7 into 0.5, so it will be 3.5 microseconds. Total T states multiplied with the clock period. So this is how we calculate the execution time of an instruction if it is given, and we can easily draw the timing diagram. Also, if we know that what are the machine cycles are involved in that and how many T states they are required. Now next machine cycle we have in 8085 microprocessor is memory write machine cycle. This cycle is executed when the processor wants to write a data byte into the memory of the into its memory. So this cycle is executed by the processor to write a data byte in a memory location. It also requires 3 T states, just like the memory read. It's a memory write. Only difference is that of the read signal and the write signal. Otherwise, the T states and the timing diagram, they are same. So let's see the timing diagram for this memory write machine cycle. We will require 3 T states. So this is the timing diagram for the memory write machine cycle. You can see that this is the clock. Here we have shown one clock period is equal to 1t state, and this is our higher order bus. So it is having the higher order memory address. Then we have lower order address bus, which is multiplexed with the data bus. So when this ALE signal is high, it means this will act as an lower order memory bus, and when this is low, it means data is available on this bus. Then for the memory write machine cycle, because it's a memory operation, so this signal input output and memory, it will be low, indicating that it's a memory operation, and it's a memory write. So we have S1 equals to 0 and S0 equals to 1, because it's a write operation. Now here we have WR, the write signal, and this write signal is low. It means it is active. Is an active low signal. So this active low signal, it is during this period, so this data will be written into the memory. So this was our memory write machine cycle. You can see that this cycle, it requires 3 T states. Now let's take an example of an instruction which is using this memory write machine cycle. We have an instruction in microprocessor as STA2065H. Okay. Now this instruction, it is written at the memory location 2010. The STA, it has the opcode 32H. Then at 2011, we will write the lower order address 65. Then we will write the higher order address at the next memory location 20H. So you can see that this is a 3-byte instruction because it requires 3 bytes to get stored in the memory. So the cycles associated with this instruction, because the execution of this instruction, it will require various machine cycle. First machine cycle will be opcode fetch. In this machine cycle, opcode fetch, it requires 4 T states. We have already studied that opcode fetch require 4 T states, and this opcode 32H, it is fetched by the processor. Now second machine cycle will be memory read. In this machine cycle, the address 65, which is stored at this location 2011, it will be read by the microprocessor. So it requires 3 T states, and this 65H will be read by the microprocessor. Then third machine cycle will be again memory read, because this higher order address 20H, which is stored at this memory location 2012, will be read by the microprocessor. So again it will require 3 T states for this 20H. Now this instruction says that store the contents of the accumulator at this memory location. So suppose at accumulator we are having 08. So this will be stored at the memory location 2065H and 08. So when the microprocessor has first fetched this opcode 32H, it is knowing that this operation is this instruction means to store the contents of the accumulator at the memory location. So it requires two things. It requires the memory location where the contents are to be stored, and also it requires that content, that data which has to be stored. So address, it has already got in the memory read cycles, in these two memory read cycles. Now it requires the data. So it is going to write that data into the accumulator. So fourth cycle is memory write. which require 3 T states. And in this cycle, memory write cycle, this data 08 will be written into the accumulate at this memory location 2065H. Okay, so total T states required will be 4 plus 3 plus 3 plus 3, that is 9 plus 4. It will require 13 T states in total, and the timing diagram will consist of the 4 T states of the opcode fetch, 3 T states of memory read, 3 T states of the second memory read machine cycle, and 3 T states of the memory write machine cycle. So in this memory write machine cycle, the timing diagram we have studied, here we have the data, so it will be the 08, and this 08 data, it will be written into the memory location 2065, which is available at the higher order and the lower order address bus. So this is how the memory write machine cycle works, and it generally occurs in 3-byte instructions which are requiring the write operation for the memory. Now next machine cycle is input output read machine cycle. Now, just like the memory read machine cycle, it was the read operation performed on the memory. Here we have the read operation performed at the input output ports of the 8085. So this cycle, input output read machine cycle, it is executed by the processor to read a data byte from the input output port or from the peripheral. Peripheral means input output devices which are connected with the 8085. So those peripherals are either from the input output port. If the microprocessor wants to read a data byte, then this machine cycle is executed. Now here we have written that the peripheral which is input output map in the system. This mapping we will read when we will see the interfacing of the 8085 with the various peripheral devices. So there we are going to understand that what is input output mapping and what is memory mapping. So this cycle, it requires the address, because here the input output port and the peripheral devices, they are going to have a particular address. So this cycle will require the address of the ports or the peripherals. Now here we have written this input output mapping. So in input output mapping, the peripherals and the input output devices, they are having 8-bit port address. You have seen that all the memory address, they are of 16 bits. But in input output mapping, the port and the peripherals, they will have the 8-bit port address. So this 8-bit port address, it is placed both on the lower and the higher order address bus, and this machine cycle, it requires the 3 T states to execute the operation. So let's see the timing diagram for this input output read machine cycle. As it requires 3 T states, so we will draw here 3 T states for it. Again, we have the clocks here. Then we have the higher order address bus. So here the higher order address will be available. Here the higher order address will be the input output port address, because input output devices are concerned here. And also on the lower order address bus, we will have the port address. As this is an input output read machine cycle, so this input output and memory signal, it is 1, indicating that it's an input output operation. And then we have S1 equals to 1 and S0 equals to 0, because this is a input output read machine cycle. Then we have read signal. Read signal is low. It means this data, it has to be read from the port which is given here, whose address is available on the higher and the lower order address bus. So from that port, the data will be picked, the read from the processor, and then the operations will be performed on that 8-bit data. So this was the input output read machine cycle. Next, we have the input-output write machine cycle. It would be same just like this machine cycle. It will also require the 3T states, and instead of read signal, we will have write signal. That means the data which is available here will be written into the port whose address is available on the buses. So we will have the same. Next cycle we have is input-output write machine cycle. So this cycle will also require the 3T states. So here this cycle is executed when the processor wants to write a data byte to the input output port or to the peripheral, which is again input output mapped in the system. And it requires 3T states, so its timing diagram will be same, only the difference is of the write signal. So this is the input output write machine cycle. You can see that the write signal is low here. So whatever data is available here, it will be written into the port address which is on the higher order and the lower order address bus. This dashed line, it is showing that at this in this period the bus, it is in the high impedance state, and because it is an input output operation, so this signal is 1, and S1 and S0, they are 0 and 1 because it's a write operation. So this is the timing diagram for the input output write machine cycle. So you can have here that input output write and input output read. It will be the timing diagram for the in instruction and the out instruction. Because what the in instruction is doing, it is getting the data from the port address which is given as an operand here. Suppose I in 08H is written here. So 08 is the port address, and this port address, the data byte which is stored at this port address will be read by the processor. So this input output read machine cycle, its timing diagram can be taken as the timing diagram of the in instruction. Similarly out, suppose we have here 04H. So this 04 is the port address. Now from that port, the data byte will be whatever data byte is there with the processor, it will be written on this 04 port address. So data byte is written at the port address. So this will be the input output write machine cycle. So the timing diagram which we have studied for the input output machine cycle, it will be the timing diagram for the out instruction also. So in this video we studied the various machine cycles, that how the instruction is executed in the processor, how its execution takes place. There are various machine cycles associated in, and for those cycles, the 5 machine cycles we studied, first was opcode fetch, then we studied memory read, memory write, input output read, and input output write. So whatever the conditions of the signals and the address bus, data bus, they are shown in the timing diagram, and we studied the timing diagram for all the 5 machine cycles. So I hope that this topic is clear to you, that how the instruction is executed in 8085 and the timing diagram of the various machine cycles in 8085. Thank you.